Today, we would like to introduce you to our work on unsupervised semantic segmentation through depth-guided feature correlation and sampling. Our intuition is simple. In contrastive learning, we want to map feature vectors for objects of the same class closer together, while drawing apart the ones from different classes. We observe many of these distances to be already present in the depth space, and therefore propose to use it as a guidance modality to guide the feature space over unsupervised semantic segmentation model. If our guidance is successful, the feature space will be learned to contrast features from objects, guided by the distances present in 3D space. To achieve this, we propose the following architecture. We build upon Stego, a work by Hamilton et al., to distill features from crops of the same image, of K and N selected images, as well as random negatives. We show the case of intra-image crops here. The image is cropped into two areas. In the following, these crops are encoded by a frozen feature encoder, a Dyno-Vision transformer, to produce a feature map. Random sampling is applied to the feature map, and the feature samples are further processed by a segmentation head. For both of these feature maps, correspondent tensors are formed that measure the distance from each location in one feature map to the other. We propose to further extend this knowledge distillation process by generating depth maps for each of the crops. To begin with, we convert the depth maps into point clouds and apply farthest-point sampling on them. This allows us to more uniformly sample the feature and depth space and collect samples where depth gradients are steep. The sample locations are then converted to 2D locations to sample from the feature maps. Further, we sampled those same locations also in the depth map to enable depth feature correlation. For this, we again build a correspondence tensor, but this time the depth correspondence tensor. All three tensors go into the loss. There, among other things, we aim to learn to align the distances from the depth correspondence tensor with the segmentation head output tensor. We call this depth feature correlation. Farthest point sampling is integral to our method. For random sampling, it can happen that all samples are drawn from the same object or even at very similar depths. This can lead to a lack of negative samples in the image and to a less effective learning process. On the other hand, farthest point sampling has been shown to equally sample the 3D space, selecting locations at different depths and around depth gradients. Here's an example of random sampling, only drawing samples from the sky and missing the plane entirely. Here's that same image and corresponding depth with it, converted into a point cloud and farthest point sampling applied to it. You can see that the plane is much better covered and the entire image is much more equally sampled. Here's another example of a skier, the sky, and some trees. Farthest point sampling likes to also sample around the edges of objects. Our 1D visualization makes more clear as to why this is the case. When the depth gradient is smooth, FPS samples the space evenly, but the sharper the surface becomes, the more samples are concentrated around the gradient. These 3D locations are consequently converted to 2D samples, and after conversion, they appear around the edges of the objects. We further extend our method with an approach we call 3D local hidden positives. In their work on hidden positives for semantic segmentation, Song et al. Introduced the concept of local hidden positives by propagating signal to neighboring patches in proportion to their attention values from the feature encoder. This strategy can be problematic for our approach, since it creates the risk of depth feature correlation loss values being propagated to locations where the depth is actually completely different from the anchor location. Therefore, we propose 3D local hidden positives. Instead of propagating to patches in 2D space, we select the closest patches in 3D space, ensuring depth consistency. As propagation values, we use the normalized distances from the anchor point to all other points in 3D space and choose the 8 closest ones. It can be seen for various examples that the propagation map is more sharp and evenly distributed for a better propagation of the learning signal. Our evaluations show significant improvements in performance across a range of relevant benchmarks. For the VITS on Cocoa Stuff, we obtained the best unsupervised MIUU of any approach and coming close to hidden positives on unsupervised accuracy. Overall, our VATB model performance is the best out of all in the table. On cityscapes, we're able to improve upon STAGO by around 8% in unsupervised accuracy and 2% in MIOU, outperforming all other baselines. And finally, for Potsdam, we're able to further increase the unsupervised accuracy to over 80% for our VITS backbone. When visualizing our predictions, we see that our method is able to correct the prediction of STAGO for images with visual irritations. In the case of the building with the mirroring surfaces, STAGO fails to correctly segment the scene. Through the use of depth information, we are able to smooth out the surface of the building, providing a better segmentation. Also, one could fear that a depth feature correlation makes the model overfit to structures obtained from the depth map. This example is a clear indication that this is not the case. Our method is able to significantly improve the segmentation, a result of the successful distillation from depth into the feature space. But also the child and the baseball are nicely separated, despite them having the same depth. Furthermore, our method is able to detect the green bush that can be seen through the hole in the fence, something that is not reflected in the depth map. Cityscapes paints a similar picture. With our method, we're able to improve the segmentations for images where there are visual irritations like shadows on the road. We further want to highlight the impact of our individual contributions. As can be observed from the table, each of the individual techniques improves the performance of STAGO. But it's when these methods are used in combination that they really unlock their potential. The use of farthest-point sampling further amplifies the learning signal for depth feature correlation, since the sampled depth values are more diverse. Furthermore, with the addition of 3D local hidden positives, we are able to significantly boost the model's unsupervised MIOU. Thank you for watching.